If you could replace human soldiers with robots, would you? Well, that is the mission of Foundation. They recently introduced the Phantom MK1, a humanoid robot designed specifically for military operations. Standing about 5 feet 11 inches tall and weighing about 176 pounds, the robot is built to handle dangerous battlefield roles such as reconnaissance, bomb disposal, logistics support, and hazardous material handling. The company has already deployed 2 Phantom units to Ukraine for real-world evaluation during the ongoing Russia-Ukraine war, making what may be one of the first battlefield tests of a humanoid combat robot. The Phantom MK1 relies primarily on on-camera based vision systems and proprietary cycloid actuators that provide strength, quiet operation, and safe interactions with humans. While the robot can navigate and perform tasks autonomously, lethal decisions remain under human control. Foundation plans to scale production rapidly, aiming to manufacture up to 50,000 units by 2027. The robots could eventually be utilized in both military and industrial operations. And the best components to be utilized in engineering designs are available from Mauser Electronics. The Omron R88M-K40030T is a compact AC servomotor from Omron's Accurex G5 series, designed for high-precision motion control and industrial automation systems. It delivers 400 watts of rated output, a rated speed of 3,000 RPM, and a 1.3 Newton meters of continuous torque, with peak torque up to 3.8 Newton meters for rapid acceleration. The motor operates on a 230-volt supply and includes a 17-bit absolute encoder for accurate position feedback. Its 60mm square flange and compact frame make it suitable for robotics, CNC equipment, packaging machinery, and other high-performance servo applications requiring precise positioning and smooth motion control. Check out Omron's R88M Servomotor today by visiting Mauser.com or by clicking the link below. For more control automation education, we present David's Corner.
Thanks, Andy. There is a topic in automation that is really simple, but at the same time really complicated, and it confuses a lot of people. And that topic is the difference between NPN and PNP technology in sensors. It's derived from transistors that run inside of them, but that's not really what we're interested in. What we're interested in is how does the electricity flow to the controller that's supposed to be receiving the signal from the sensors? Well, here I've built a simple tester to distinguish whether we have a functional NPN or PNP sensor. To use this tester that I've built, I use 2 LEDs that are placed in opposite polarity to each other, because the difference between NPN and PNP is that in a PNP sensor, electricity, conventional current, flows from the sensor to the controller. But in the case of the other sensor, the NPN, the electricity flows from the controller to the device. So a diode, an LED, being a one-way flow of electricity, can help us distinguish whether we're working with an NPN or PNP sensor. So I will connect first a PNP sensor. This is an ultrasonic sensor with a PNP output. And using a spare lead, I can connect it to either power or ground of the power supply to be able to see whether the LED lights up. When I connect it to ground of the power supply, I see the red LED light up, meaning that the electricity is flowing from the sensor to the ground of the power supply. That means that this is a PNP sensor. On the other hand, if I connect an NPN sensor, I can try to connect the electricity to ground, nothing will happen. But if I connect the electricity to power, I can see the green LED light up, telling me that electricity is flowing from the positive of the power supply through the sensor back to ground. So it's a simple experiment using a few benchtop components that I had, but I can easily test whether the electricity is flowing from power through the sensor to ground, or from the sensor through negative back to ground of the power supply to be able to tell the difference between whether I'm working with a PNP or NPN sensor, or as a simple test to make sure that the sensor is working properly the way it should. Andy, back to you.
Thank you, David. All right, it's time to adjust your knowledge gains in our SmartBit quiz with our 3 control automation questions. The questions are scored using actuator output percentage, and today we'll be testing your knowledge on our friendly HX7 robot lost in the jungle. Let's begin with our first question for 25%. Recon robot HX7 powers up deep in a jungle clearing. Its sensors immediately argue about where the robot actually is. The camera thinks it's near a rock, the IMU thinks it's falling over. The LiDAR thinks everything is a tree. HX7 must decide how to combine this chaos. Is it best to A. Let each sensor estimate position separately and compare later, or B. Fuse all sensor data in real time using an extended Kalman filter? And the answer is B. Fuse all sensor data in real time using an extended Kalman filter. An extended Kalman filter fuses multiple noisy sensors to produce a reliable position estimate. Okay, let's move on to our next question worth 25%. A monkey leaps out from a tree and bumps HX7's shoulder while stealing its antenna cover. Oh no! HX7 must stabilize itself. Is it best to A. Increase proportional gain dramatically, or B. Use a disturbance observer to compensate for the external force? And the answer is B. Use a disturbance observer to compensate for the external force. Disturbance observers estimate and reject unexpected forces. Okay, let's go on to our last question worth 50%. While climbing a hill, HX7's hip actuator must respond quickly without losing stability. Is it best to A. Use a single position control loop, or B. Use cascaded torque, velocity, and position loops? And the answer is B. Use cascaded torque, velocity, and position loops. Cascaded loops improve response and stability. Want to try again? Just click the link on your screen and be sure to check out our other AE videos for the latest in control automation.